Centennial is a great time to look back, 100 years to the park, 160 years to some of the early adventurers and explorers, and it's also a good time to look forward. I think that's the benefit of looking back, is to think about lessons learned and where we're headed. So I want to do that today with respect to geology. How many geologists out there? Okay, not enough. Geology is a marvelous science, study of Mother Earth. What a good planet we live on, and what a worthwhile task to try and understand the processes that go on the Earth and her history. And so we do that with various tools, the most modern tools, and also rather boots on the ground sort of efforts. And I want to say that the Geologic Map, we've been talking about mapping this session, fantastic presentations. Geologic Map adds another dimension or two. It takes a topographic map, or DEM, which is itself, we've been hearing, an endeavor to produce accurate ones and beautiful ones, and it adds to it a time dimension, because the rocks that are at the surface of the Earth each have their own age and history, and it also adds a depth dimension, because the layers are horizontal in the upper part of the Grand Canyon, they're tilted in the Grand Canyon Supergroup, and they're folded wildly in the basement. So this map here, which by the way, Huntoon et al., the best-selling geologic map of all time, now out of print. It's a tragedy it's out of print, but it gives us an opening for next steps in terms of mapping. So I want to kind of go back to the beginning of this is probably not comprehensive, but it's my perspectives on stages that we've come through in terms of geologic mapping. I got to do scales for a minute. So I don't know if you've noticed, but if you go out and walk on the surface of the Earth, there's something there everywhere. Yeah, so that's your job as a geologist. You have to say what it is, and you also have to say how it got there, how its orientation is, a little bit about its age, and you can do it at a variety of scales. Here's a geologic map of the United States, a beautiful thing by the USGS, 1 to 2.5 million, not exceptionally detailed, but a really nice view of our whole country. And the colors represent different rock units of different ages, and you can dive into that and learn the history of the U.S. Here's the Arizona map, 1 to a million state map, and so you can put more detail on these maps, 1 to a million, than you can at 2.5 million, but you don't have the whole big picture. So this is going to be kind of a theme. It's a trade-off. Do you want to get the whole picture, or do you want to see the detail? Are you a forest or trees kind of person? And the upper box there, the Grand Canyon, I just want to highlight George's 9 quadrangles that are shown there in the black boxes. Now we're coming right to the end, really. George has just finished these efforts of putting together the picture of those 9 quadrangles that encompass what we think of now as the Grand Canyon, the entire Grand Canyon. So I'll get back to those, but those are at 100,000, 1 to 100,000. A lot of times the mapping's done at much more detail than that, and you compile then at 1 to 100,000. So looking back, let's see, 1 to 62.5, that's the Dragon map, the blue map, the Huntoon and Wenrick Billingsley maps in the Western Grand Canyon, 1 to 48,000. And then the Timmons and Karlstrom map over there on the right is the first one of these 1 to 24,000 maps that we have out and behind. But let's go back a little bit to the first one that I know of, and people have shown this one from the Ives Expedition, beautiful map. I got this from Matt, thank you, Matt. But you notice I put the rocks in the bottom so you could see them a little better. These guys did an amazing job for their time and for the struggle to be out here, and they identified the different colors represent the different ages of rocks, and for the most part they got it pretty good. They got tertiary and quaternary volcanics, and they got the basement. They thought the Grand Canyon Supergroup was Silurian, but hey, that's not too bad. And they thought the rim of the canyon was Pennsylvanian instead of Permian, but But they had fossils, they looked for fossils, they did a great job of figuring out basically what the rock types were. And you know, the theme about these topographic maps that we've been hearing about, I've been thinking about it as I hear these talks. We just call them base maps. We go out there, and because we're trying to put the rock types on these topo maps. But you can see if you look at this history, how when a new set of topos come along, the geology takes off, because you have a better way to locate yourself on the map, and you can show more detail. So this is Dutton's topography. Pretty good. This is actually almost a 61 to 63,000 map. It's pretty good topography. This is from the Dutton folio. You can see the Grand Canyon looks like it should now, because Powell has been through. They have the different ages. The Grand Staircase, that's the most elegant depiction of the Grand Staircase, as the Mesozoic rocks are being stripped back off the blue Kaibab limestone by erosion. And you see the volcanic fields, a really nice map in 1882. He had different scales all within that same folio. This is more or less 1 to 250,000 in that same folio, showing a little more detail. And so ages aren't right, but we're beginning at this point 150 years ago to know the basic rock types, the fossils in them, and the distribution of rock layers. Here's the Mathis Evans topographic map we've been talking about. And as this was being produced, along comes Levi Noble, who actually is putting geology on that new Shinemu quadrangle map. And so he worked a lot on the Grand Canyon Supergroup, the tilted layer in the lower right, and defining faults. And he also clarified quite a bit about the stratigraphy, getting the ages and the nomenclature better. By about 1935, the rock names, for the most part, had been kind of settled. Here's a map from Maxon, 1961, 1968, two versions, Geologic Map of the Bright Angel Quad. He had a title of Collaborator at Large with the park. So I don't know how he got that, but anyway, the park needs to think about, and of course Eddie McKee was a park naturalist, and as we look forward and we look back, we say, okay, what's the park's role in any of this? And hopefully that will be improving in the subsequent years. But this is an elegant geologic map. You can see the fault lines along the Bright Angel Fault, northeast trending, and Maxon's rock column from 1961. You know, the layers in the right thicknesses and the ages and the names are pretty far along. That rock column has been reproduced again and again in different iterations for a lot of years. And I gave a talk last week about depicting geology in terms of rock columns, and that was a very influential one. Cross section at the bottom. The geologist's always trying to map what's on the surface and then use the measurements that you take to interpret what is underground. And so the cross section at the bottom shows the three sets of rocks: the basement rocks at the bottom, the tilted Grand Canyon Supergroup, and the flat-lying Paleozoic rocks on top. Again, a step forward in terms of mapping the photogrammic methods, and we're taking advantage by people. This is kind of interesting. I ran across this in our library. You probably have it here, but Maxon in 1969 did what he called a preliminary geologic map, and it has almost no new detail on it, but he was obviously starting big to do what then was taken over by Peter Huntoon and George Billingsley and other collaborators. And these are the, this is, what is this? This is, here's Maxon's map in two sheets, following on the new topography and trying to compile everything he could with not much detail in the west. But this map, we call it the blue map, or I sometimes call it the dragon map. Anybody heard that term for this map, the dragon map? Okay, as you look at it, do you see a dragon or not? Okay, this is kind of an argument between me and my wife. about the dragon. Okay, so I want you to think where you think is the mouth of the dragon, and what are those two things sticking up and pointing to the right, and here's the two interpretations. I won't tell you whose is whose, but there's the two interpretations of the dragon map. So I don't know which one was yours. Do you think that the two things sticking up are the mouth, or do you think they're the ears? Anyway, so that's a diversion, but best-selling geologic map of all time. And you know, one of the successes of this map, I give to the creators of it, George and Peter Huntoon, and they brought in people who wanted to work on different parts. And so the early versions, let's see, what do I have? I can't remember all the iterations, but this is the 1996 version that I was privileged to be co-author on because we did the basement rocks. And prior to that, there'd been a different group that had their basement lines put on there. Jim Sears mapped the supergroup, and George is always concentrated on the stratigraphy and everything else. Peter Huntoon did a fantastic job with faults. And so this map represents not only the best knowledge at the time, but a team effort to put together a best view of Grand Canyon geology. Then they extended their work to the west with the, I like to call these the Huntoon et al. Brown maps because they didn't color them. And boy, do I like that when I'm out hiking or working with students. I can see the topo lines. But then George came along and Karen Wenrick and did the maps in color for the USGS. So same scale, 1 to 48,000, quite good detail, and covering really the western part. So here's George's effort following on from that. Each one of these geologists, myself included, George included, takes advantage of all that hard work from previous workers. It's a lot of work to hike through the Grand Canyon. If you're hiking, it's a lot more work if you're mapping, trying to look behind each rock, what's over here. There's something on the surface of the earth everywhere, and you have to go look. And so it's a lot of work. I've had a lot of students involved in it, a lot of PhD students. I've been mapping in the Grand Canyon geologic mapping for 35 years. George is like 55 or something, so he's my hero. But this is the Grand Canyon sheet, one of 9 sheets. And if I tried to show you the detail that's in there, we could zoom into whatever your favorite place is and find out what the faults look like and the ages of the rocks. But this is the big picture. And I've kind of gone the other way now in my present emphasis, and that is I want the big detail on a small area. So this is Mike Timmons, PhD student of mine, and I put together this Eastern Grand Canyon map, 1 to 24,000. And so that piece of paper that you get it on is about the same size, but you just have a lot more detail. So that's kind of the effort that I've been doing. This is the Timmons and Karlstrom map, and there's a lot of stuff on here on all geologic maps. There's an explanation of the rock units with the oldest at the bottom. There's a rock column and a time column to show you ages and rock names. All those cross sections, you know, you make slices and think what the 3D geometry is of these rocks. And so it's a big effort. So that's a PhD student's effort with a lot of support from multiple collaborators, because that's the way you get the best geology. Here's the cross section. This is a fun one because you may know the Butte fault, which is that big fault angled. Well, there's 4 of them there, but the second one from the right is the Butte fault. And if you look at the bottom brown layer, you can kind of find one of those brown layers you can trace from the lower left across the fault to the upper right. You can see that the left side is down, right? Agree with that? But then if you look at the Kaibab and all the Paleozoic rocks that are kind of projected into the air, you see that the left side is up. So you see, do you see what I'm saying? That fault, the geologist really screwed up. Didn't even know which way the fault moved. No, that's not true. What's true is that that fault was a left side down fault in the Precambrian, huge amount of displacement that allowed these basins to develop, the Chuar group. And then later on, when the continent was squeezed, that weakness, that zone of weakness got inverted and pushed up the other way. So it's called fault reactivation. It's a nice story of how a weakness in the earth can be reused again and again. If you break your arm, you might break it again at the same place later on. So I just want to touch on a couple of topical things. As we map, we're interested in the history of the earth, and we're interested in the record, everything we can learn from these rocks. The rocks are the historians, and we're taking the record. This is Powell's drawing, slightly modified, of the three sets of rocks. Now if you look on the right from the Timmons and Karlstrom map, you can see, if you get good at reading maps, you can see the three dimensions and you can see the ages all in that colors of that map. And I won't go through it in detail because I just want to highlight some of the things we've learned from 35 years of mapping. Here's what I want to do before I retire and get those, most of the mapping's done, so we just have to pull together the Upper Granite Gorge, that's Brad Ilg's PhD, Middle Granite Gorge, that's several students, the lava dam work from Ryan Crow, and the first thing I did was the Lower Granite Gorge, and it's still not published yet, so that's terrible. But those are going to get done at 1 to 24,000, and so here's an example of a geologist out there trying to put lines on the map, which rocks are where. The red on the map on the right, the red stuff are the pegmatites, if in case you're wondering. So you do some sky mapping where you sit there and sketch, just like Matheson and Evans, but then you go put your nose on the rock and identify it, and you take it back to the laboratory and date it and study it in various which ways. So these will be 1 to 24,000 detailed maps, but I'm just showing them in cartoon form. And sometimes geologists, like when I started, I didn't care at all about any rocks except the basement rocks. So we would blast down the river till we got to the Precambrian. I just didn't care about any of those other things. And how the canyon got there, who cares? I was interested in that one set of rocks. So you can make a map that just shows what you think the basement is doing, and that's what this is for the lower gorge, and there it is for the upper gorge, with folds and foliations and shear zones, and the record of how the North American continent was first assembled almost 2 billion years ago. So that's a story in that rock layer. Or when Mike Timmons came along, I said, okay, I'm pretty much done with the basement, except I haven't published it yet, but let's do the supergroup. So we said, okay, let's peel everything off, get rid of that ugly basement, and just show a map of the Grand Canyon supergroup. Oh, this has the basement in it too. But the supergroup is green and dark purple. And Powell, of course, saw the Unkar group along the river, the green color there. But there's no record that I know of that he saw the Chuar group. It wasn't until Walcott came along where he went back in there, and he thought he was going to find a Burgess Shale kind of record in the Chuar group, which didn't come out, but he did find these millimeter-sized microfossils that he called Chuarias. So we have a rich record of Walcott's paleontological work in eastern Grand Canyon. So thinking forward about these maps, I'm just, what happens when you come at a time in your career when things are changing? We heard about that from Tom, and you want to adapt and you want to pull it in together. And so visualizations that we're going to be able to do increasingly is a challenge, though, because not only is the topography a challenge, but all these layers of different rock types are a challenge. And then this is the thing that's really a challenge, the zoomability. Now in Google Earth, we can zoom in and we can see more and more detail as you zoom in. Well, that's the future of geologic mapping. But we have to have every one of those scales well understood for that scale. You can't show everything on the big regional maps. And so you see the little red box there. So this is already the 1 to 12,000 detail, 1 to 24,000 detail, and then that map showing the rock types along the river in more detail. So I don't know how we're going to quite get there, but we will. And then these beautiful maps, these that we saw, how they're presented, we can use them for earth science education, science literacy, and actual important discussions about park resources. So this is from Lori Crossey's talk that she's giving. Those we take that oblique view, and we put the faults on there, and we say,
okay, where does the water move? Where does water move from the North Rim snowpack into the springs and across the canyon? So we can begin to convey to park officials and resource people a little bit about how the geology affects water resources and hence and water quality, and hence the future for park development. So this is the park now. The park now goes from Lake Powell to Lake Mead. And George has a map of it, 1 to 100,000, which a lot of which would take quite a bit of enlargement because it was done in detail. But we have this chore now of portraying that and educating a public that's increasingly sort of resistant to understanding concepts of time and science. And so geology's a way to hook people in. The Grand Canyon's a way to hook people in. And I want to implore all of us to do what we can to add science literacy to this thinking of the mapping conference. So 160 years of geologic mapping. Geology's been in the forefront of Grand Canyon science for 160 years. New geologic mapping often follows these developments in technologies like topographic maps, and now with digital media, it's going to be the same. It goes hand in glove with the science questions, the ages of the rocks, the layers, the new dating, and how to manage resources. And here's what I want to see: near future mapping. I want to get those 1 to 12 to 1 to 24,000 maps finished, that we have the mapping done from this hard student work, and get the fault networks mapped better, because that's the water pathways, we think, in large part. And then how to display them. You know, there's no geologic map at the Yavapai Geology Museum, and also the Grand Canyon GCC, Grand Canyon Conservancy, doesn't sell geologic maps anymore. They're big, and how do you sell them? They're hard to stack in the back and keep rolled and whatever. But we need to get geologic maps back out into the public. I think people love them. They're beautiful, and figure out how to do that, and use that as a way to work on science literacy for this 6 million people a year from all over the world. So I think we have a task to do. Thanks very much.
We've got a few minutes. Does anybody have any questions? Geology questions? Got a few minutes.
Could you describe the age of the rocks that you have from the rim all the way to the base layer?
Yeah, we can just forget the break, and I'll go. The basement rocks are almost 2 billion years old. They represent the formation of the continent. The tilted rocks, Grand Canyon Supergroup, range from about 1.25 billion to about 700 million, and they record the assembly and breakup of the supercontinent of Rodinia from the perspective of a place, Grand Canyon area, that was inside of the supercontinent. So it's a sedimentary record. The last flat-lying rocks start at about 520 and go to 270 million. So that's most of the Paleozoic or old life period. The rocks of the dinosaurs, the Mesozoic, have been stripped back off the rim of Grand Canyon. And the Cenozoic, the era we're in now, there's a few little scabs and interesting rocks of basalts and travertines around. So we have an amazing record of the last half of Earth history, about 2 billion years.
I have a question. That was loud. For the layers of the soils in the Grand Canyon, or I guess just in geology in general, were you saying you guys have to kind of guess, or how does that work for figuring out all of what's underneath? Do you have specific tools for that, or how does that work?
Yeah, how do we time rocks? Basically, there's two ways: relative ages. I'm older than you, so we know that. And then there's absolute ages. We'd like to know how many years old you are and how many years old I am. For that, we use radioactive clocks, radiometric dating. And there's a variety of methods, and they test each other, and we're getting much more refined absolute ages or numerical ages for rocks using systems like uranium-lead decay in zircon crystals, for instance. But the fossils that come from the relative dating are the way we always start. And so the bottom sedimentary layer is older than the one on top of it, and then they get younger as you go up. And then the fossils change as life on Earth evolved through millions and millions of years. So the fossil record was the way the geologists originally set up the geologic timescale. And now the dating is getting very precise about when the fossil transitions took place.
Thank you.